Welcome back, everybody. In this video, we're talking about prime factorization, which is a tool that we can use to help us simplify fractions. It's also kind of intrinsically interesting and has other applications, but our main purpose of it is to look at it to help us to simplify fractions. So let's get started. So to talk about prime factorization, we should talk about what factorization is and what factors are. So that's where we'll begin. So we want to talk about finding a number's factors. So what factors are numbers that you multiply together, create some other number. So easiest way to see this is by example. You can think of 12 as 3 times 4. 12 can also be thought of as 2 times 6. So 3, 4, 2, and 6 are all factors of 12. They're numbers that divide into 12. Other examples, 20 is not very interesting, but it's 20 times 1. Okay, any number is equal to 1 times itself, and so that's not very interesting, and in general, we'll kind of skip that possibility. 20 is also 2 times 10. 20 is also 4 times 5. So 1, 20, 2, 10, 4, and 5 are all factors of 20. 20 is also 1/2 times 40. If you're not so comfortable with the half times 40 thing, that's okay. But the point I was going to make here is when we talk about factors, we're talking about whole numbers that divide into another number. We wouldn't say that 1/2 and 40 are factors of 20. Factors are whole numbers or counting numbers. Okay, so we can skip that possibility. Okay, so numbers that multiply together to create another number are called factors. The word factor here is used in 2 different ways. When we say finding a number's factors, that's the noun, the person, place, or thing, right? And that's describing those numbers that you multiply together to create another number. When in the second sentence, to be able to factor a number, here when we use the word factor here, there we're using it as a verb, which is an action word, meaning to do something, right? The act of factoring a number is finding those factors, right? So here when I wrote down 12 is equal to 3 times 4, 12 is equal to 2 times 6, I was factoring 12. There's more possibilities, right? I should have also said 3 times 2 times 2. So there's a few ways, at least, that you can write down a factorization or factoring of a number. And being able to do this is helpful in simplifying fractions. And so that's why we're talking about it primarily. So that's what factoring a number is. So as you've seen here, there's a couple of different ways I could write down factors for 12. It turns out that there's a particular way that is especially useful and interesting to us, and that's prime factorization. So we have to talk about that next. So prime numbers. So there's a lot to read right here. So let me stop talking for a second. All the counting numbers higher than 1 fit into one or of 2 categories. They're either prime or composite. A prime number has no interesting factors, I like to say. Any number is divisible by itself and 1. 40 is divisible by 40. 40 divided by 40 is 1. But nobody cares, right? That's not a very interesting fact to say. 40 divided by 40 is equal to 1. I just picked 40, okay, there was nothing special there. And any number divisible is divisible by 1, right? 23 divided by 1 is 23. Any number is divisible by itself and 1. Okay, so that's not very interesting. If those are the only things it's divisible by, itself and 1, then it's a prime number. Here's some examples of prime numbers, 2, 3, 5, 7, 11, and so on. 17, for example, 17 is what times what? The only way to finish that is to say 17 times 1, right, if you're using whole numbers. So there's no other way to write down a product that equals 17, where the product is whole numbers. Okay, so that's what makes it a prime number. In contrast, composite numbers can be factored in some other way. For example, 15, in addition to saying 15 times 1 is 15, nobody cares. 3 times 5, right? That's another way of factoring 15. 21, 3 times 7. 33 is 3 times 11. So these have other factorizations. That's what makes them composite. Okay, a couple of things to notice. Out of all the prime numbers, 2 is the only even prime number. All of the other even numbers are composite because they're all divisible by 2, like 170. Okay, 170 is divisible by 2, so it's automatically a composite number. Okay, so 2 is the only even prime number. Also, not every odd number is prime. So that decision about even and odd is not the same as composite versus prime. You can see that a lot of the prime numbers are odd. Composite numbers are all the even numbers except for 2, and then a bunch of odd numbers. But not every odd number is either prime or composite. So 9 is 3 times 3. It's odd and composite. 19 is odd and prime. Okay, so at this point, you should be able to figure out whether a number is prime or composite for any number under 100. Okay, if you have any question on what that means or whether a number is prime or composite, let me know. Okay, so let's try it a little bit. We're to decide if each number is prime or composite and then explain. So give like just a simple explanation of the reason for our choice. Okay, so pause the video, try this yourself, and then restart the video and see how you did. All right, so 16 is composite. And you could have said, well, 16 is 4 times 4, or 16 is 2 times 8. Okay, those two facts make it so that 16 is composite. Okay, 31 is prime. Okay, and here, if you really wanted to beat it up, you could say, list every possibility, less than 31. But 31 is just 31 times 1. There's no other number that divides into 31. 49 is composite. And it's because 7 times 7 is 49. Okay, all right. So at this point, you should know the difference between prime numbers and composite numbers. Out of all the different ways of finding a factorization for a number, the prime factorization is one that is especially useful or especially special. And that's where the factorization consists just of prime numbers. For example, earlier I had told you that 12 was equal to 3 times 4. And that is a factorization of 12, but 4 is composite. If we factored 4 as 2 times 2, now that is a prime factorization of 12 because all the factors that you see listed there are prime numbers, 2 and 3. Okay, as another example, let's go with 36. 36 is boring because it'll all be all 3s and 2s again. Let's go with something a little more spicy, like 48. That's going to be the same. That's okay. No, 40. 40 is fun. I like 40. Okay, so 40 is 4 times 10. All right, that is a factorization, but neither 4 nor 10 is prime. So let me keep factoring. 4 is 2 times 2. 10 is 2 times 5. Okay, so 2 times 2 times 2 times 5 is the prime factorization of 40. Usually we would write that with exponents. So we'd say 2 cubed. 2 is used as a factor 3 times, and then 5. Okay, so 2 cubed times 5. Okay, an important fact is that every whole number greater than 1 has exactly one prime factorization. So where we saw that 12 could be 3 times 4, and 12 could be 2 times 6. Yeah, sure. If you go as far as prime factorizations, there's only one answer. Okay, if you keep breaking down the number as far as you can, you will get only one final answer. Okay, so we're going to try a couple of these. There's basically 2 ways of showing your work here. It doesn't really matter to me which way you do it, so it's kind of personal preference, and I'm going to show you both. Okay, so let's try 30 first. Okay, 30 is 10 times 3. So I'm going to split this into 30 as 10 and 3. This is going to end up looking like the roots of a tree, so it's sometimes called a tree diagram for factoring, but you can call it whatever you want. Okay, 3 is prime, so I'm going to leave it alone. 10 factors as 2 times 5. None of 2, 5, and 3 factor anymore, so we are all done. So what's at the ends of the roots makes up our factorization. It's 2 times 3 times 5. Okay, 36 is next. 36 factors as 6 times 6. And each of the 6's factors as 2 times 3. Okay, so that's 2 factors of 2. So we'll say 2 squared. And then 2 factors of 3, we'll say 3 squared. So that's it, 2 squared times 3 squared. Okay, so before I do 105, I wanted to mention here for the 36, you probably thought, okay, 6 times 6. But let's say that you didn't. Let's say you said, well, I kind of thought of 3 times 12. Is that okay? Well, 3 times 12, yeah, sure, let's try it. 36 is 3 times 12. 3 is prime, so I'll leave that alone. 12 is it 3 times 4, 2 times 6? Doesn't matter, just pick one. Let's go with 2 times 6. 6 is 2 times 3. Okay, the blue one definitely looks different from the green one so far, but let me go ahead and write down my final answer. There are 2 factors of 2 and 2 factors of 3. That's 2 squared times 3 squared. Notice that that is the same as what we got before. Earlier I had said here, every whole number greater than 1 has exactly 1 prime factorization. When you get all the way to the bottom, when you get to the final answer, it's going to be the same. That scratch work with the tree is going to look different, perhaps, but the final answer will be the same. Okay, 105. 105 factors as 5 times 21. Okay. If that took you a minute, that's okay. All right, I'm going to show you in a few minutes how to figure that kind of stuff out faster. Okay, 105 is 5 times 21. 5 is prime, so I'll leave it alone. 21 is 3 times 7. So this leaves us 3 times 5 times 7. Okay. All right, so we're almost finished with this. I have just another couple more things to show you. Here, the work for the prime factorization, I had done using a tree diagram. The other way of doing it is through basically repeated division by primes. And I'm going to show you how to do that first with number 30. So this will be just the other way. Usually people like the tree way here that I've shown you, but not everybody does. So let me show you another one. Okay, so here we're starting with 30. This one is going to be repeated division. We're going to start with primes. We're going to start with the smallest prime, which is 2. So 30 divided by 2 is 15. So I divided 30 by 2. I've put the answer up top, got 15. Okay, is 15 divisible by 2? No. So what's the next prime number? The next prime number is 3. Does 3 divide into 15? Yes, it does. 3 divides into 15 5 times, and 5 is prime. Okay, so that's the end of it. What do we have outside? 2, 3, and 5. That is our final answer. 2 times 3 times 5. Okay, so let me try that next with 36. So 36 is divisible by 2. 2 goes into 36 18 times. 2 goes into 18 9 times. 2 doesn't go into 9. So what's the next prime number? The next prime number is 3. 3 goes into 9 3 times, and 3 is prime. So then looking along the outside, we have a 2, a 2, a 3, and a 3. That gives us our 2 squared times 3 squared. Okay. So now, last one with 105, and then we'll be done. 105, not divisible by 2, so I'll skip that. Next one is 3. 3 goes into 105. That one you might not have guessed right away, and that's fine. And it will be 35. 105 divided by 3 leaves 35. 35, not divisible by 3. So what's the next prime? It's 5. 5 goes into 35 7 times. And there's our 3, 5, and 7 on the outside. Okay, so my personal choice is the tree diagram way because you get some flexibility in it. Like with this 105, it was for me easier to see 5 times 21 than 3 times 35 makes 105, for example. But to each his own, whichever factorization you like is okay with me. Because again, you're going to get the same final answer no matter what. There's exactly one prime factorization for this. All right, so that takes us to the end of this first part on prime factorization. We'll see a little more of this in the second part. In the meantime, let me know if you have any questions, and have a great day.